Alright, so we're going to go ahead and get started with Lecture 5, Part 2 of this lecture on entropy. In our last lecture, we looked at the essential questions for this particular lecture. What must occur for a chemical reaction to be spontaneous? And we actually addressed that question and answered it in Part 2. And remember, we said that in order for a chemical reaction to be spontaneous, two things can occur. One is that it can be an exothermic process where heat energy is being dispersed into the surrounding environment. And remember that when heat is being dispersed into the surrounding environment, it increases the disorder or chaos or randomness of the surrounding environment. But in the chemical process, we could also be creating more disordered matter. And so when matter is being disordered or becoming more disordered, and the energy is creating a more disordered environment or surrounding universe, then a chemical reaction will become more spontaneous. And so we looked at delta S, which is the change in entropy. And we said that when systems create a more disordered surrounding environment, the entropy is increasing. And when a process creates a more ordered surrounding environment, then the entropy is going to become lower. And so high entropy means more disorder, and low entropy means more ordered, and that's really important. Okay, in part 2, we're going to go ahead and address this last essential question, is what are the indications if an entropy change of a system is going to increase the disorder of the surrounding environment. So how do we know? If we look at a chemical process, how can we tell if the entropy is going to increase, leading to a more spontaneous process? So that's what we're going to address. And so if you go back and you look at your lecture handout notes, turn to question number 6, and we answered that last time. It says, what is the second law of thermodynamics? And we stated that the second law of thermodynamics is the total entropy, the total amount of entropy of the universe increases in any spontaneous process. Again, that's saying that if a spontaneous process is going to occur, then the amount of disorder in the universe is going to also increase. And this second law of thermodynamics is one of the most important laws in all of science. Alright? So now let's go ahead and look at question 7 then. And question 7 goes back to our second essential question. How do you determine in an entropy change of a system is increasing the disorder of the surrounding environment? Okay? So we have a few categories in your notes here. All of these are important for you to know and know very well, and they will lead to for you to predict or make predictions if the entropy is going to increase in the system. Okay, so let's take a look at this. Remember that if matter is becoming more disorganized during the process, then the entropy is going to increase. But if the matter is becoming more ordered, then the entropy is going to lower. Alright? And the same thing, if we're releasing energy into the surrounding environments through an exothermic process, then it's creating a more disorganized system. At the same time, an endothermic process is going to absorb energy from the environment, creating a more ordered environment our surrounding universe. Okay, so those are some things to think about as we go through this. Okay, the first one, I think you can look at this as an obvious. If a solid melts to form liquids, what's going to happen here as far as entropy train? Well, if a solid is an organized piece of matter and a liquid is more disordered, then the entropy should increase as we go from a solid to a liquid. And so we would simply say that the delta H, or the delta S for this, is going to be positive. Okay, so a positive sign indicates that the entropy is increasing. Well, let's look at the next one. Solids or liquids vaporize to form gases. Well, gases are the most disorganized matter out there. So if we are moving from a solid or a liquid to a gas, it's definitely increasing the entropy. So it's going to be positive. Solids or liquids dissolve in a solvent to form more non-electrolyte solutions. Okay, this is also going to be a positive delta S, because when we're dissolving things, there's going to create more disorganized or more randomness in most cases. So it also creates a positive delta S. So far all of these are creating positive entropy changes or increasing the disorder of the universe or surrounding environment. A chemical reaction produces an increase, and I'm going to highlight this or underline it, increase in a number of molecules of gas. This is really important, and you're going to see this on the test, I guarantee you. That when you see that we're going and creating more gas molecules during the process, the delta S is definitely going to be positive for this process. Okay, now we've already addressed exothermic processes, and we said exothermic releases heat energy into the surrounding environments, creating a positive delta S, or increasing the entropy of the universe, more disordered. And then finally, heating a substance is also creating a positive delta S, creating more disorder or randomness in the universe. Alright, so the best thing to do is to look at some examples and see if we can kind of look at these examples and decide, does this process create more disorder in the universe? So therefore, is it increasing the delta S? And remember, if it is increasing disorder, then the delta S is going to be positive. But if the universe or the surrounding environment becomes more ordered, then the delta S is going to be negative. Alright, got those signs? Okay, so let's look at the first one. If we had something like bromine, and it is a liquid, and then we're going to change bromine into Br2 into a gas, then what is going to be the sign for delta S? You should have said it's going to be positive, because going from a liquid to a gas increases the entropy of the universe, or it's becoming more disordered. Remember, a gas is more disordered matter than a liquid. Alright? Okay, so let's look at another example here. What if we had two copper solids plus oxygen gas, and we're going to create 2 copper oxide solids. Okay? So now, to understand this problem, we have to look at the states of matter again. So we're going to go from a solid and a gas, and we're going to create a solid. So the gas is more disordered than the solid state, and so the universe is becoming more ordered. So our delta S for this process should be negative because we're losing our gas and making a solid. So the entropy should be lowering, or get a lower entropy. Alright, let's look at another one. If I have silver ions, and they're an aqueous solution, plus let's do some bromine ions, aqueous solution, and we end up creating silver bromide solid. What is the sign for delta S? Is it becoming more ordered or more disordered in our universe? Well, remember that solutions are more disordered. So we're going from a more disordered solution to a more organized solid. So therefore the sign should be negative for this particular process. Alright. Alright. Oops. Let's look at some other possible examples here. Let's say that we're going to go from H2 gas plus Cl2 gas, and we're going to 2HCl gas. Alright, now here all the states are gases. So now we're going to look at the number of gas molecules on each side. So on the reactant side, we have 1 mole of hydrogen gas and 1 mole of chlorine gas. So that gives us 2 moles of gas on the reactant side. But we also have 2 moles of gas on the product side. So what is the sign for delta S? Well, in this process, because we're creating 2 moles of gas, and we started with 2 moles of gas, the essential change is 0. The delta S is not changing. So in other words, the system is not becoming ordered, nor is it becoming disorganized. It's essentially staying the same in this process here. Now, however, what if instead of creating 2 moles, what if it turned out that we were only, theoretically, even though this is not true, we were only creating 1 mole of gas? Alright? If that was the case, we're going from 2 moles of gas to 1 mole of gas, then the system, or the surroundings, essentially becoming more ordered, because we're losing gaseous moles of gas. So we'd say the delta S is going to be negative in this case. Alright. Alright, let's look at another scenario that could arise here. Let's take a look at say CH4, which is a gas, and we got 2 moles of oxygen gas, and we're going to create a mole of CO2 gas plus 2 moles of water, liquid water. Alright, so what's occurring here? Notice that on this side we have gases and we have creating a liquid. So just by that alone, we're going towards from a gas state to a liquid state, so the surrounding environment should become more ordered here. Also, if you think about it, we have on this side 3 moles of gas, 1 mole from methane and 2 moles from oxygen, giving us 3 moles of gas, where on the product side we only have 1 mole of gas, and that's from CO2. So we're definitely creating a more ordered system, or delta S. Oops, let me erase that. Delta S is definitely going to be, not positive, it's going to be definitely negative. The entropy is being lowered, or the universe is becoming more ordered system. Okay, and this is an important reaction to look at, because there's 2 things you can look at: the number of moles of gas on both sides of the reactants and products, plus the fact that we're going to a liquid here. Alright. Alright, let's take a look at one more example before we go on here. Alright, so let's say we have copper 2 ions, aqueous, and it's going to react with zinc, solid zinc. And it's going to form copper solid plus zinc ions. Alright, what do you think the delta S for this reaction is going to be as far as the sign? Is it going to become more ordered or more disordered? Well, if you said it was going to become more ordered, you would be wrong. And if you said it was going to become more disordered, you would also be wrong. It is essentially not a change whatsoever. Why is there no changes? Because we're going from aqueous to aqueous and solid to solid. So there's no change in the order and disorder of the surrounding environment. So essentially 0. Alright, so there is several examples that we can look at in order to predict if there's going to be an increase or a decrease in the disorder of the surroundings during a chemical process. Or in other words, to determine if delta S is positive or delta S is negative. And the bottom line is, if delta S is positive, then the entropy is going to increase, right? P increases, it goes up. But if delta S is negative, then the entropy goes down, decreases. And so this right here creates a more disordered state. And that's what we want, is a more disordered state for a process to continue to spontaneously occur naturally. Alright? Now, this is a lot, I know, and I would seriously go back and re-look at this video and replay it. You're going to need to know how to do this for the quiz to predict the sign of delta S for any process that I give you, whether it's positive, negative, or not changing at all. Okay, so go back, look at these examples, look at this video, think about this closely. The bottom line is, if we're going from if matter is going from a more ordered to a more disorganized, obviously the sign is going to be positive for delta S. If we're releasing heat energy in an exothermic process, delta S is going to increase. So again, make sure that you go through those. Alright, the last thing we're going to look at is how do we calculate the entropy for a reaction. So now we can predict the sign, but how do we actually calculate the value? Well, the equation is something you should be somewhat familiar with. We've seen this with using delta H before of a reaction. This, though, instead of finding delta H, we're going to find delta S of the reaction. And you already know what the naught means for this. The naught there, you know that means under standard reaction conditions or standard conditions, which I have told you you need to know for the test. So make sure you know what the naught means in this equation. Alright, so simply to find the delta S naught of a reaction, or the entropy change of a reaction, is you take the sum of the moles of the products times the delta S naught of the products minus the sum of the moles of the reactants times the delta S naught of the reactants. Okay, so let's say that we have a reaction. Let's do C2H4 gas plus H2 gas, and that's going to produce C2H6 gas. And we need to know what the delta S naught for this reaction is. Well, looking at the reaction, you should be able to predict what the sign is going to be. Notice that you're going from 2 moles of gas, here, 2 moles of gas, that's from the C2H4, and the 1 mole of H2 going to 1 mole of gas. So if we're going from 2 moles to 1 mole, then the system, or the surrounding environment, should be becoming more, that's right, ordered. So we would assume that the sign, the overall sign for this should be negative. Or in other words, the universe is becoming more ordered. Alright? So this is probably, the way it's written right now, is not very spontaneous. Okay? But let's see if we can actually calculate what delta S is going to be. Well, what they're going to give you on the test is they're going to give you the delta S naughts for each one of those substances. Alright? So for instance, if we look at C2H6, that delta S value, in fact, is, let me re-erase this so we can kind of look at this. Let's list everything first. Okay, so we got C2H6, we got H2, and we got C2H4. And so the delta S values for each one of these, which again will be given to you, this one is 230, this one is 220, and this one is 131. Right? And the units, by the way, are going to, basically for S values, or delta S, or S values, or in joules per mole Kelvin. Okay? So these units are very important to remember, that the delta S values for each one of these are in joules per Kelvin, mole Kelvin, joules per mole Kelvin. And this is different because in delta H there are kilojoules per mole, but here it's going to be joules per mole Kelvin. Okay? So now let's throw these into our equation up above. So we're going to start out with the products first. So we're going to start out with C2H6. We're going to go 230. And how many moles? 1 mole, right? 1 mole of C2H6, and that's our only product there. So we're going to take this and we're going to subtract it from now our reactants. And so we're going to take the sum of the actual reactants. So let's take hydrogen, which is 220, and we're going to multiply that by 1 mole of hydrogen, and then we're going to add that to 131 times 1 mole of C2H4. And so when you multiply here, and you multiply, and then add our reactants together and subtract everything, we should find something like this: 230 minus 220 plus 131, and that should equal to a negative 121 joules per mole Kelvin. So our delta S value up here should be 121 kilojoules per mole Kelvin. And notice it's a negative. We calculated it to be a negative value, which is what we also predicted it should be based upon our predictions. Alright? So you should be able to use this equation right up here, this all-important equation. Make sure you know it really, really well, not only for the quiz, but for the test. There's going to be several of these problems. We're going to give you some homework problems so that you can practice this, but essentially it's just like using this equation for solving delta H. These values here will be given to you for the test or the quiz, and then you just plug and chug those values in there. Okay? So yeah, I think it's pretty simple and straightforward. That's all you need to do. Alright, so that's all for Lecture 5 on entropy. Again, there's a lot here, so I would replay this video, both Part 1 and Part 2 again, dissect this, and be ready for the quiz that's going to happen in class. Make sure that you can answer those essential questions. Make sure that you are able to predict if delta S is going to be positive or negative. Make sure you understand the second law of thermodynamics really well. Make sure that you can calculate delta S using this reaction that we just went over. Alright? Also, make sure you understand the definitions of spontaneous and non-spontaneous processes, because those will all be on the quiz as well. Alright, and that will be it for now.